Dear students, in last video we have discussed about the diffraction due to enceladus or diffraction grating, in which we have derived a formula of resultant intensity, uh, distribution of intensity, in which we have discussed about the principal maxima, minima, secondary maxima, and also we have learned about the ratio of secondary intensity, secondary maxima, and principal maxima. In this video, we will learn about the spectra and absent spectra and maximum number of orders. Now, we will start grating spectra. We know that grating equation is E plus D sine theta equal to n lambda, where E plus D represents grating element, theta angle of diffraction, small n number of orders of spectra, and lambda is wavelength of monochromatic wavelength of light, incident light. And we know that when a wave of wavelength lambda falls normally on a grating, principal maxima are formed in the direction which is given by E plus D sine theta equal to n lambda, and n may be 0, 1, 2, 3. And from this equation, it is clear that for a given order n, the angle of diffraction theta varies with respect to wavelength. And the longer the wavelength, the great angle of diffraction becomes high. Hence, if the incident light is white, then each order will contain principal maxima at different wavelength in different directions. The principal maxima of all wavelengths corresponding to n equal to 1 will form the first order spectra, and so on. The principal maxima of all wavelengths corresponding to n equal to 0 will, however, be along the same direction theta equal to 0. Hence, zero order zero order maximum will be zero order maxima will be white, having on either side of it the first order spectra, second order spectra, and so on. Most of the light is concentric in the zero order principal maximum, and the intensity goes on decreasing gradually as we have to the higher order spectrum as shown in grating spectrum. It is in this axis we can represent intensity, it is zero order principal maximum, and this is first order principal maximum, and second order principal maxima. These are secondary maxima. Secondary maxima. And it is secondary minima. And similarly, in left side, this is first order principal maxima, second order principal maxima, and this is secondary maxima. And similarly, these are secondary minima. This is the representation of spectra for diffraction grating. Now we will move towards the absent spectra. Absent spectra, the spectra which will absent during this process, as we know that the resultant intensity is given by A naught square sine square alpha upon alpha square sine square n beta upon sine square beta. Now we know that in previous video we have determined the condition of principal maxima is E plus D sine theta equal to n lambda. This is condition of principal maxima in grating spectrum. Suppose it is equation number 1, and where n represents the number of order of spectrum, and condition of minima in single slit, it should be E sine theta equal to m lambda. This is condition of minima in diffraction due to single slit. Suppose this is equation number 2, and where m may be 1, 2, 3 and so on. If both conditions are simultaneously satisfied, a particular maximum of order n will be absent during the satisfaction of these two equations in the grating spectra, and these are known as the absent spectra. The order which will absent in spectra, that is known as absent spectra, or we can say the missing order of spectrum. And suppose we divide equation number 1 by 2, it becomes E plus D sine theta upon E sine theta equal to m lambda n lambda upon m lambda, and we can calculate it. Sine theta cancel out, lambda cancel out, E plus D upon E equal to n upon m, and E represents the slit thickness and D represents the separation between two slits. This is grating and this is slit thickness E, and this is the separation between two slits D. And if separation between two slits is equal to the slit thickness, then the above equation, suppose equation number 3 becomes E plus E upon E equal to n upon m, or we can say 2e upon e equal to n upon m, n cancel out, n equal to twice m. It means for m equal to 1, 2, 3, first, second, third order, n becomes 2, 4, 6. It means when the width of transparencies and occupancies of the grating are equal to each other, separation between two slits or and thickness of slits are equal to each other, then second, fourth, sixth order spectra are missing, or we can say remain absent. Similarly, we can calculate when D is equal to twice E, separation between two slits is equal to twice of slit thickness, then it should be this D is equal to 2E. It means E plus 2E upon E equal to n upon m, or we can say 3E upon E equal to n upon m. E cancel out and n becomes equal to 3m. It means when m is first, second, third and so on, n becomes 3, 6, 9, or we can say for first, second, third order of m, third, sixth, ninth order spectra will be absent. This is the absent spectra. Now we can determine maximum number of orders which is visible in a grating by the help of grating. Maximum number of orders, which how much number of orders we can see by a grating. To determine the maximum number of orders, we take grating equation. We know that is E plus D sine theta equal to n lambda, again where E plus D represents the grating element and theta diffraction grating, small n number of, suppose small n represents the number of maximum order, and we want to determine the maximum number of orders, small n, it should be equal to E plus D sine theta upon lambda, and maximum possible value of theta, it may be 90 degree. The diffracted angle, suppose this is slit and this is angle theta, incident ray, diffracted ray, and now angle of diffraction is increased. Now angle of diffraction is increased, angle of diffraction is increased, and maximum angle of diffraction, it may be 90 degree. It means maximum possible value of angle of diffraction, it should be the 90 degree sine theta, and it means when sine theta is maximum, n becomes maximum, or we can say n maximum equal to E plus D sine 90 upon lambda, or we can say E plus D upon lambda. This is the maximum number of orders. And if grating element is less than 2 lambda, if grating element is less than 2 lambda, then n maximum number of orders less than 2 lambda, it means less than 2 lambda upon lambda, 2 lambda upon lambda means 2, less than 2. It means if value of grating element is less than 2 lambda, then maximum number of order becomes less than 2. Less than 2 means only first order is visible. When we use a grating of which having grating element less than 2 lambda, then only first order is visible for normal incidence. That is the maximum number of orders. Okay, thank you very much. In next video we will discuss about the another topics of diffraction grating. Thank you.